My homework assignment was the brain 101, but again, this is not our classic brain structure, anatomy kind of thing. We're going to take a little bit different approach, take a different journey, end up the same place, but along the way I think maybe we can change the way we look at it, which then changes our perspective on why we do what we do. So if we start with a very simple question, what is reality? And I will leave it at the fact that I doubt any one of us can come up with the same definition of that, primarily because it's actually a very difficult thing to define. Timothy Leary, as he states, the universe is inside your brain. One definition of reality would be that the world or the state of things as they actually exist. But that raises a question, how do we actually define as they actually exist? So one way to think of our nervous system and our brain is that of a reality-defining system. For example, Mona, let's say you and I get a call from Mr. Musk, SpaceX. He says, look, we're going to explore this whole new planet. We've never been there before. You guys are brilliant at this stuff. I want you to design the sensor unit that we're going to drop in there and tell us all about that environment. Which is really what we do in our environment, but in a little different way. So if we thought about it, we would obviously need to be able to identify characteristics of the environment. We'd need to be able to communicate that information in one way, shape, or form. And then we'd have to have some way to evaluate and react to that incoming information. Kind of the basics of what it takes. One of the reasons that our realities are all very different has to do with how we measure what's out there. If I take an example of electromagnetic energy, we all know that we are constantly bombarded with all types of electrical magnetic energy. My father, who is an astrophysicist, made his living building eyes, sensors, for satellites to detect gamma rays. If you notice, this is what our sensors are able to accommodate. A fraction of the entire spectrum of it. How does our system do that? Well, we have a sensor, a measurement device. We call it the eye. That's just a term that we kind of randomly came up with, which takes that energy in and then ultimately converts it into an electrical signal. And that's key because every sensor that we have ultimately translates that information, that data, into an electrical signal. And that's what we work with, are these electrical signals. If you look at sound waves, the spectrum of the frequencies, tremendous. We again deal with a very small proportion of it. A sound wave is a pressure wave, but again, there's data, there's information within that pressure wave. So when I speak, I'm expelling air. My vocal cords are vibrating, set up these pressure waves. I don't sound like Pavarotti because I'm not that skilled in creating that pressure waves. But somehow magically, I put information, I put data into those pressure waves. You guys have receptors that are tuned to that frequency. You can decode that data, that information, and do something with it. So it's kind of a very fundamental teleportation in a strange way, because I can take part of myself, send it out there, and whoever happens to be around with a sensor can pick that up and internalize that. So again, it's a way to communicate with our environment, to interact with our environment. Ultimately, gets translated into yet another electrical signal. In the case of the ear, it's a tympanic membrane, which is nothing more than a vibrating system. That vibration magically creates an electrical signal that gets wired into a certain portion of our brain. Again, just to point out the fact that what we perceive as sound, again, that's a term that we've just agreed to come up with, has no intrinsic meaning to it, is a fraction of the entire spectrum of that energy. Young people typically hear in the range between 20 hertz and 20 kilohertz, but notice how much we're missing out there. So just using those two senses, we can see, and you can kind of follow me here, that it's very hard to come up with any kind of standard definition of some independent reality. We all create our own reality based on information that we gather, how we decide to gather that, and how we decide to process it. So we create our own reality. There's no true realities. My reality is different than your reality, different than your reality. Now, sometimes that reality generation works well. Sometimes it doesn't work as well as we might like it to. So, if you think about the brain as what part of the system that we have all this electrical activity coming up, and the brain can be considered as the central processing unit of our system, manage the incoming data, routes the data to the appropriate areas of the brain for processing, and generates some type of response from the organism. There's a couple of key points when you think about the brain. First off, the wires that transmit that neurons. That's all. And all neurons are basically the same thing. There's not very much uniquely different about neurons. So the wiring is very consistent throughout the system. And the brain itself is nothing more than this huge collection of these neurons. So it's the same electrical wiring. Buried within that collection are innumerable pathways, think of them as highways, that are parsing and sending this information into various regions of the brain to do whatever needs to be done with it. The various regions of the brains that carry out certain tasks are very specialized in it. However, there is nothing unique about those regions of the brain. If I look at the part of the brain that processes sound, grossly, it looks exactly like the part of the brain that processes sight. Under the microscope, they look the same. They are not unique physically. So there's something different about it. It's hard to put your finger on it, but it's important to know that there is nothing unique about one part of the brain versus another part of the brain. We've all seen pictures of brains where they have the nice color. They say, well, this is the motor cortex, this is the sensory, this is the homunculus. And it would lead you to believe that those parts of the brain are designed just for that job. But in fact, that's not the case. We have to remember that we're constantly bombarded by just truly an unfathomable amount of information from our environment. Our measuring devices, our sensors, certainly place tight limits on how much of that information actually is collected. But despite that, there is still an overwhelming amount of incoming information that the brain has to process or is being asked to process. If you think about it in real estate terms, huge demand, limited supply. So there's a constant kind of angst set up in that system. Tremendous demand, growing demand, fixed supply. The Mars rover that we're designing, because we're very smart, we realize that if I'm going to design a system that's going to operate in a strange environment, it would be really smart to make sure that system had an ability for adaptability and to improve its efficiency. Our brain does have that capacity, obviously. Historically, up until not many years ago, we were all taught that the brain was a static system. I mean, how many of us grew up being told, you're born with 1 million neurons, every time you sneeze, 100,000 die, you're never going to get them back. There's a fix. So the concept of neurogenesis, the creating of new neurons, is a relatively recent phenomenon to be accepted in more global terms. It's been recognized for many years, but the folks that were presenting that believe that were sidelined by the more standard medical folks, if you will. The same with neuroplasticity. So 10 years ago, when we started doing this, when I would use those terms, blank looks. Nowadays, it's kind of entered to the general conversation, if you will. They're not such unique terms. So again, nothing could be further from the truth, from the belief that our brain is a static system, and that is key, and it's fundamental to what we do. If it were a static system, we wouldn't do what we do because there would be no point in it. It wouldn't work. So neuroplasticity, by definition, is the ability of the brain to change itself. The question is, how does the brain know how to do this? And it's really based on a positive feedback system. Now, throughout the universe, positive feedback loops are used for lots of reasons, just like its cousin negative feedback loop. If the analogy I like to use is basically the more a certain portion of the brain is being utilized, the more processing it's doing, the better it gets at doing that. So years and years ago, to get from here to Beaufort, we walked along a trail. When there was enough traffic, that trail got a little bit bigger, a little smoother. Then buggies came along, it turned into a track. Cars come along, now it's graded, then it's paved, a second lane gets added, a fourth lane gets added, street lights come on. All that infrastructure gets added to the more that pathway gets used. And that's the same process that works in our brain. The more we utilize a pathway, the easier it is to use that pathway, the more efficient that pathway becomes. This is why it's very, very difficult to break a habit. Habitual thinking. Think about, depression. People have recurrent negative thoughts or whatever. It's because that pathway has become so reinforced that that becomes the default pathway. So to change behavior, I have to go against what my brain is trying to tell me, which is, no, this is the way to go, when instead I want to go this way. If you watch me play tennis, you'll realize I'm horrible. I'm not very efficient. I got limbs all over the place. I'm missing it. You watch Yvonne Lindell play, smooth, very efficient, no wasted movement. Because those sensory input, motor output pathways have been utilized over and over and have become so efficient that he doesn't look like me because I've got all kinds of inefficiency built into my tennis game, whether it's tracking the ball coming in, whether it's knowing how soon do I need to get over there, how to get, all this stuff has to happen. And that's why I look like an idiot playing tennis, but somebody else looks quite skillful. It's all because of this neuroplasticity. The whole idea about neuroplasticity and neurogenesis, again, as I said, is relatively new. There's been phenomenal experiments along the way that have demonstrated it and shown how it works. An example would be if I took my arm, put it in a neoprene sleeve so I had no sensory input, and I mobilized it, tied it to myself. Then before too long, the sensory cortex that was responsible for taking all that incoming sensory data and the motor cortex that was responsible for moving it will be underutilized. So the neighborhood, if you will, starts breaking down. There's potholes aren't getting fixed, streetlights are broken, abandoned buildings. Well, the neighborhood next door, though, the next county over is booming. It's doing great. So what does it do? Guess what? I'm going to move over and take over this real estate. Neurogentrification, if you will. So one neighborhood blight, the next neighborhood, because there's always demand. There's too much demand for the real estate. So anytime there's any kind of opening, if you will, well, we're going to move over and take over that real estate. So before long, those same nerves, those same area that was moving my arm is now involved in something else. One of the better examples of this, there's a group of folks who have a problem with their cochlear nerve, so their vestibular system, how they know where their head is in space, has been injured, doesn't work as well. So they constantly feel as if they're falling, which would be a horrible sensation, I think. I do like the fact that their support group, they call themselves the Ramblers, the Wanderers, because they can't walk in a straight line very well. But one of the early and really fundamental studies that demonstrated that the different brain can do different things, somebody much smarter than I, took these folks, put like a football helmet on with some motion detectors on them, through a computer, processed, sent a signal out to a little electrical strip that they could put on the tongue. So these motion sensors were connected to different parts of that strip on their tongue. So when they tilted their head, they got a signal somewhere on their tongue. Almost instantaneously, their vertigo went away. Almost instantaneously, their brain was able to figure out, wow, that information that was coming in through this part is now coming in off of my tongue, and then be able to figure out how to integrate that and utilize it. So that was exciting. They would put it on, they wouldn't be wobbly, they'd take it off, they were wobbly. What they noticed was that the longer they wore their little anti-wobble helmet, the longer the duration that the vertigo was gone when they took it off. Until after around 20 or so treatments, it was gone completely. So the brain rewired itself, if you will. Now, if you looked at those brains under the microscope, you couldn't see any difference. There was nothing really, truly, fundamentally different. But I use that as an example to point out how incredibly efficient our brain is at utilizing space that's available to process information and to prioritize information to process. So those people's brains figured out, you know what, I don't really need to be worried about taste as much as I need to be able to figure out where my head is in space. So I'm going to usurp my tongue homunculus, and I'm going to start using that as a where am I in space information.
Can it double up?
Interesting question. Can it double up? It is very difficult to double up. We use the term multiprocessing a lot in today's society. In fact, there is no such thing as multiprocessing. I think we all know that. We cannot do more than one thing at a time. We can switch very rapidly between lots of tasks, which is what has been called multitasking, but it's not. It's single tasking a lot quickly. So this idea, your brain can basically kind of do intentionally one thing at a time. Now, can the same part of the brain be utilized to do different functions? And that's an excellent question. It's really hard to actually tease that out because it's very difficult to truly define on a microscopic level what part of the brain is actually doing what. We're certainly getting better at that.
Maybe not necessarily the brain itself, but like if the tongue was able to establish the equilibrium, were those same people able to still use the tongue for taste?
The taste, it turned out, was blunted, but it didn't go away. So the brain was able to parse that and say, gosh, I'm going to get more than one type of information come out of that. So the region of the brain that was in charge of taste still managed the taste.
So feasibly they could put sensors on the back of their neck,
Yeah,
and
but
the
it-
taste would come back, and it would be something on their neck.
But absolutely. So again, the take-home message on that is this huge collection of nerves that we call a brain. There is nothing about those regions that's unique. And that's so fundamental because what that means is if you can identify an area that needs to be ramped up, I increase the demand, and then it's going to respond. I mean, if you look at current day classic treatment, post-stroke rehab, it's the most nihilistic thing you can imagine. So I have a stroke, my right arm doesn't work. What's the standard of care now? Passive movement. Doesn't do a darn thing. All it does is exercise a physical therapist. It has absolutely nothing to do with stroke rehab. But there are certainly lots of studies that shows that, you know what, if I do that differently, if I force that part of the brain that was damaged to actually get back in the game, that you can recover a lot of that lost function. But you have to understand how the brain works, and you have to understand this plasticity before you can design an intervention that's going to be successful. Moving on to brain anatomy, I'm going to leave the details of a lot of the brain anatomy for later folks to chat about, but I kind of want to look at it in a more holistic view, if you will. There's a term called the triune brain. I'm not sure if anybody's familiar with that. It was coined by Dr. McLean, developed this model of the brain based on evolutionary development, the idea being that there's actually 3 separate brains that had developed under evolutionary pressure, each of which kind of has a different goal and different function. I accept that. I'm going to add to that a little bit as well and expand that just a bit. So again, the triune brain theory, it's a paleontological, whatever that word is, approach. The idea being that each of the layers of the brains were established over time to face evolutionary pressures. They each had different skills and jobs that were required. The 3 main layers, we talk about the reptilian brain, we talk about the limbic system, and the neocortex. Again, the reptilian brain, the paleomammalian, or the limbic system, and then the neocortex is the cap, we think, of the cortical structures. So the reptilian brain, the first of the ones that developed, can be defined as I eat and kill, therefore I am. So the reptilian brain consists primarily of the brainstem and the cerebellum. Main job is physical survival, if you think about it. Cerebellum, which is this weird thing that sticks off the end, regulates and modulates motor activity. All of the fundamental functions to survive, digestion, reproduction, circulation, temperature maintenance, this is what allows us to be warm-blooded. All of these things are managed within the reptilian brain. Again, on a more holistic point of view, the reptilian brain perceives the world without higher thinking. There's no emotion involved in reptilian brain function. Dinosaurs didn't have to define the context of what was happening. Under the guidance of the reptilian brain, animals simply experience and react to it. This is why animals, and so we talk about how they handle pain so much better than we do. Well, they have a different processing system for it. For thousands of years, obviously, the reptilian awareness predominated. The reptilian brain is actually very reliable, but it tends to be a little bit rigid and a little bit compulsive. There's not a lot of flexibility in the reptilian brain. Moving up the order, the mammalian brain, or the so-called limbic system, hugely important for what we do. Hugely important for what we do. So the main structures of the limbic brain are the hippocampus, the amygdala, hypothalamus, performs an even bigger job of helping us survive, focused on the 4 F's of survival, if you will: feeding, fornicating, fighting, fleeing. So the mammalian brain could be thought of, I hoard and I mate, therefore I am. So this is the job of the mammalian brain. This is the part of the brain that wants us to provide shelter. It's the part that wants to protect our young. It's the part that seeks partners for procreation. It's also the part of the brain that records memories. Memories of actions that led to favorable outcomes and unfavorable outcomes. This is the operating center, and I'm going to say this again and point to it, that's responsible for generating every self-limiting belief that we have. This is where self-doubt comes from. This is low self-esteem, guilt, fear, scarcity. All of those come from that limbic system, particularly the amygdala, which we'll get to. Many, many people that you can look around and see, you can see, are operating with the limbic system in the driver's seat. 5 out of the 10 commandments are basically mandates to rein in our limbic system. Killing, adultery, stealing, bearing false witness, coveting. All of those are limbic system issues. The amygdala, as I mentioned, that's a small almond-shaped structure. It's really responsible for those instantaneous responses to incoming information. This is the part, the threat assessment center. So when threat is perceived, bam, fight or flight, like you said. Cortisol floods it. Interestingly, when that happens, higher brain centers are taken offline. This is why in this crisis situation, stress situation, reason goes out the window. This is why people's performance doesn't work as well when they're in a high stress situation. It's why my basketball game goes all get out when there's a high stress, because that fight or flight, that fear, that anxiety floods the system, the higher brain gets taken offline, and we now become a slave to this amygdala telling us there's danger. Interestingly, the amygdala, the limbic system, cannot tell the difference between a real event and a recalled event. So a memory that you recall will stimulate the same response as a new event. So your brain can't tell the difference between what's actually happening and what it creates. Which is interesting if you really think about it, because not only do we create our own reality based on how we interpret the world, but we also create our own reality because our brain has no way to tell the difference between something it's generating and what's being fed in. So when we meditate and we say, go to your peaceful place, but we don't actually go to our peaceful place, but the fact that I can recall that, I can generate the same response, right? So again, that's hugely important in terms of our ability to do what we do. The brain cannot tell the difference between a recalled event, an imagined event, and a real event. Again, going back to the very first question, what is reality? And if you really ponder that under the Right, pharmaceuticals, that becomes a very interesting discussion. So the neocortex, the most recent evolutionary layer, the cerebral cortex, this is the thinking part that we kind of think about that. Comparing it just over the spectrum, looking at sizes, I just have a picture of the mouse, the monkey, and the human. Obviously, it's increased in size. Includes frontal lobe, temporal lobe, occipital lobe, parietal lobe. Those are the main parts of the cortex. And this really is what separates us from lower order animals, if you will. So, the neocortex, I think, therefore I am. So we've gone from I eat and kill, therefore I am, I hoard and recreate, now I'm thinking, and therefore I am. Neocortex added language and communication, which enhanced our survival skills. It's a part of the brain that can comprehend time, which is very important. This is why lower animals, dogs, for instance, I love my dog thinks I'm gone for eternity every time I walk out and come back in. No concept that it was only 30 seconds. That's why she's incredibly happy to see me every time I walk in. Because from her perspective, I've been gone forever. This is the part of the brain that allows us to get out of the structured physicality of the here and now. This is the part of the brain that allows us poetry, music appreciation, being able to contemplate universes other than ours, big thoughts. You can imagine that poetry was not a great survival skill back in the day on the plains in the savannah of Africa. However, these were the ingredients that ultimately led to where now is the wisest, not just the strongest, that got the most fertile women, got the most shekels, were able to succeed. So that was an evolutionary drive. And again, very important. Think again, how many people function out of their limbic system? Their upper cortex is offline, so they really are not utilizing a tremendous evolutionary advantage and resource that they have available to them because they're slave to their limbic system. Now, they're not doing that on purpose, and they don't know that's happening, and they don't know how to not do that. That's one of the things that we offer. I can understand that. We at Brain Advantage, we spend a lot of time working on all kinds of different parts of the brain, whether it's the temporal lobes with hearing, occipital with eyesight, but we put a great emphasis on working on the prefrontal cortex, and for a couple of reasons. When everything's working well, the prefrontal cortex is running the show, and the brain's functioning well. Understanding the relationship between these different brains will help understand why that's in fact the case. Another way to think about the brain geography, if you will, lower order reptilian brain, middle or the mammalian brain or the limbic system, cortex. All of us have been conditioned to think that this is a hierarchical structure. And it stands to reason that in the system that you and I designed, we would take all that incoming data, we process it, we send it to the highest order that we could, upper management would deal with it, make decisions, send out edicts, send it back down, and move on. But it doesn't work that way. So the brain is not hierarchical. It's not hierarchical. The term holon, from the Greek from whole, is probably a better way to describe these different subbrains. A holon can be defined as something that in and of itself is whole and complete, but it's also part of another. Which means that each one of these subbrains, subcomputers, can function completely independently without information from above or from below. Yet they also intercommunicate. When you have that kind of system, there's always a battle to see who's going to be in charge, who's in the driver's seat, who's running the system. And again, if we go back to the limbic system, when I'm operating out of a position of fear, my limbic system's in the driver's seat. It's taken over the system. What we're trying to do is, in some ways, balance that system out, balance it out so that that holarchy instead of hierarchy is actually a balanced intercommunicating structure that's not hierarchical. yet it's not being dominated by one subbrain versus the other. Again, the reptilian brain needs to be able to do what it does without having to worry about it. I mean, it's going to continue to keep our core temperature up, maintain our blood pressure, maintain our heart rate, without having to deal with whether or not we're finding a mate, whether or not we're eating, et cetera, et cetera. The limbic system does what it does, cortex needs to do what it does, but there needs to be some communication within them if we're going to have the most efficient little unit that we have wandering around on that planet. So each of these three subbrains can be thought of as serving the higher agenda of the prefrontal cortex. So when everything is working well, the prefrontal cortex functions as a systems integrator and as the overseer. It's the prefrontal cortex that allows us to see the world in a much different, greater light, that allows us to imagine the world from a non-ego point of view. An example would be you and I go for a nice hike up in the mountains. Your reptilian brain is in charge. We're walking up, you stumble on a tree trunk or that's in the middle of the road, doesn't even faze you, you just keep going. If you're functioning from your limbic system, then when you get back from that hike, you're going to be, that was the worst damn experience. I can't believe Randy made me go up there. How could that trunk have been in the way? The Park Service should have had it clean. My boots weren't working right. This is really, all that stuff comes up. When my prefrontal cortex is working and we go on that same hike, now when you come back and tell the story, it's a journey of epic proportions. We climbed up, we viewed these incredible vistas. We understand that I stumbled on that route. Just like journeys in life have stumbling blocks, but we can overcome them. You see the difference in how we view it? So if I'm operating out of that damn route, this is horrible, versus this was an amazing adventure. Yeah, there's stumbles along the way, but this is Homeric and it's, it's a very different way to see the world. And honestly, this is my own little advertisement, but if we're going to save our universe and if we're going to save our world, we need to be functioning from that prefrontal cortex point of view. And we need to have as many people functioning from that point of view as we can, because the limbic system point of view doesn't work. That's what's utilizing all the resources, all those things. So again, for lots of reasons, there's this fascinating consilience in my world between universe issues, individual issues. So I can't overstate the importance of the balance in that system and the role that that prefrontal cortex plays. That's why we spend a lot of time working on that prefrontal cortex. So what can go wrong with this system? A multitude of things. But if you really think about it, and again, this is a very different way about thinking about brain function than you'll read or hear otherwise. Everything that we have, everything that we perceive, everything that we do can be broken down to there's a signal coming in, some processing, and some signal going out. So the problems that can happen can, for the most part, be categorized as either it's a problem with data in, a problem with data manipulation, or a problem with data output, right? A computer is no better than the data that comes in, right? And it's no better than how it can send out that information. So in a lot of ways, you can break down what really is a myriad of brain issues into really these kind of categories. There's either something going wrong with the system coming in, how it's being processed, or how it's being taken out. As an example, if we think about dyslexia, most of us have been taught or learned that dyslexia is a reading problem. It's got to be a reading problem. It's not. It's a hearing problem. So when I'm learning to read as a youngster, very complicated. It requires an integration of sound, of sight. I have to recognize these strange symbols and somehow link them to some noise that this other person is making. So if my auditory system consists of a little tiny keyboard with only 8 notes as opposed to a full organ, it's hard to discriminate between a D and a B. They look differently, they sound a lot alike. So as I'm learning to read, and I get a little further along, I still have a hard time discriminating D's and B's. It's not because I can't see what a D looks like, what a B looks like. It's because I don't really know what D sounds like and B. I don't know what those symbols represent. There have been some wonderful studies that show if you take dyslexic kids and you work on their auditory input and you enhance the register, if you will, then suddenly their dyslexia gets better. Because it's not a vision thing, it's a hearing thing. Trying to put it, so it's a data in problem. Just an example of something that we grew up thinking was one thing, but in reality has nothing to do with our ability to see at all. So what do we do at Brain Advantage? I'm going to leave a lot of this details for further along, but again, we can think about it in a big picture way. We evaluate various sensors' function and the data generated by those sensors. We can identify problems or issues in those areas. We evaluate the data management of that information. How does the brain process that incoming information? We can identify issues with data output. How is that information that's come in and been processed, how is that manifest? And then using, obviously, a number of kind of state-of-the-art, novel, non-invasive technologies, which we'll talk much more about later, we can then intervene and help in those areas. That's an overview picture, details to follow.